In the movies, crazy scientists who build time machines are always obsessing about power. Like, it takes so many gigawatts of electricity to get the thing to work. Well, a bunch of real scientists have been working for years on one giant experiment, trying to create exotic particles that haven't existed in the universe for 14 billion years, back to the Big Bang itself. Physicist and correspondent David Work reports that, in a way, it is a giant time machine. Just like in the movies, it's all about energy.
You'd never guess that hidden beneath these French mountains, an army of workers is underground, constructing the biggest and most complex machine on Earth. It's a project that's got physicists around the world brimming with anticipation.
It's a big step. This is a big time.
We may find things which nobody has ever thought of or told us before.
It's a real adventure, because we don't know if it's going to work.
The goal of this giant construction project is nothing less than to find the basic building blocks of the universe.
The basic quest of particle physics is, what is the world made of? Do we know everything? Do we know all the constituents of matter? Do we have them all?
Scientists have already found a whole carnival of subatomic particles that make up the universe.
List some names.
Matter as we know it today.
There are protons, neutrons. That's what we're made of.
The top quark,
Bottom quark
the up,
and the down quarks.
charm quark, the strange quark.
There was a time they just named everything something silly.
There are pions, kaons,
W bosons, Z bosons.
5 different upsilon particles, lambdas,
Gluons for the strong force.
omegas, sigmas,
Muons.
Who ordered that?
and my favorite particle is the tau.
This panoply of particles is called the Standard Model, and it's our best picture of what the universe is made of. But as dazzling as it is, we know that the carnival is incomplete. There have to be other hidden particles out there, and we need a new experiment to find them.
Normally, physicists don't get to ride in helicopters, but today we want to see the world's largest experiment. And up here is really the only place you can get a sense of the scale.
Below me is the construction site at CERN, a particle physics lab. The new experiment is so big, it stretches from the mountains in France across the border to the Geneva airport in Switzerland. That's because the main part consists of a circular tunnel 16 miles around. The tunnel is home to the world's biggest, most powerful particle accelerator ever, called the Large Hadron Collider, or LHC. Because it's so big, the LHC will let us probe deeper into the stuff of the universe than we've ever gone before. This tunnel is being filled with giant electromagnets.
And in fact, you can see some of them on the ground right there.
This is my stop. Each tubular magnet costs close to $1 million. And the LHC will need more than 1,600 of them.
So what is this?
This is the magnet. This is the magnet which is inside this big blue tube.
Okay.
The magnets are designed to keep those tiny parts of an atom, called protons, flowing in a narrow beam through the tunnel. When they're all connected together into a ring, the magnets will create a 16-mile racetrack for protons.
In the ring, the powerful magnetic fields force the protons to go round in a circle. And each time they go round, they get a little kick from an electric field. So they go faster and faster, until eventually they're traveling almost at the speed of light.
And In fact, the particles, they are traveling in these two tubes. In one of the tubes, the particles are traveling in one direction, and in another tube in an opposite direction.
So there's actually two beams of particles going in opposite directions.
Yes.
One beam going one way and one beam going the other way.
Exactly.
And there's two beams because you're going to collide them.
Exactly.
This is a technique that's familiar to physicists. A proton traveling close to the speed of light, although absolutely tiny, will carry a lot of energy. Two of them traveling in opposite directions will carry twice the energy. Make them collide, and most of that energy can be released in a tiny but powerful explosion. With enough energy, the explosion should create fundamental particles that we've never seen before. If that happens, it'll be in a tiny region smack in the center of a vast underground cavern. This is one of the 4 places around the ring where the two beams will actually collide. One beam will come from a tiny beam pipe through the middle of that hole over there and fly over my head. And the second beam comes through that hole over there, and high up over my head in the middle of the cavity, the two protons will collide. Now we're colliding two tiny little protons. Why do we need this vast cavern to find out what happens? Well, in order to detect if any new particles have been created in a collision, researchers have to fill this cavern with some of the most complex scientific instruments ever created. The one here is called CMS. This is one end of the vast CMS detector. The whole detector consists of a series of these plates, each one of which is instrumented with thousands of detectors you can see up here. As we move down, you see a large number of these which will all be slid together to make the final detector. No space at all is wasted. This big hole looks like a hole in the detector, but in fact, the hole in those detectors is filled by these detectors. Different detectors pick up different kinds of particles. And sandwiched together, they'll create a single enormous cylinder which completely surrounds the point where the protons collide. That's important because as the particles fly away from the collision through the detector, they'll leave tracks which form a kind of fingerprint. It's by analyzing these fingerprints that scientists should be able to tell if a new particle was briefly created at the moment of collision.
That's why the experiments are hugely complicated. They have to identify all the things that come out of two protons that hit.
The LHC experiments are by far the most difficult that have ever been done in high-energy physics, and maybe any experiment.
In fact, the experiments are so complicated, it takes physicists from dozens of countries to pull them off.
I'm from Switzerland.
I'm from Belgium.
Sono italiana, Toscana.
France.
Japan.
Austin, Texas.
Russia.
UK.
California.
From Senegal.
New Jersey.
Colombia.
India. From Bombay.
From Germany.
Argentina.
I'm from Togo, West Africa.
I'm from Brazil. And I'm from the Czech Republic.
You meet people from all over the world. You talk with them, you get their point of view, exchange ideas. They all tend to be physicists, so it's not that wide, but I find that's exciting. If the rest of the world worked the way we do, we'd have far fewer problems.
One problem they do have is analyzing the vast mountain of data that the LHC is going to produce. Because when it's running, it'll create about 1 billion proton collisions a second. And it'll be running 24/7.
We get 40 million megabytes of data created every second.
40 million megabytes,
Right.
40,000 gigabytes, or that would be 1,000 large disks for your home computer every second.
Yes, it's mind-boggling. The amount of data that we'll be generating in 1 year is 10 times bigger than all the World Wide Web stored data.
In fact, the World Wide Web was invented here at CERN to analyze the results of earlier experiments. But the LHC has so much more data, it will need the power of the web's successor, something called the grid. Using millions of computers around the world, the grid will turn high-speed computing power into just another commodity, like music or telephone service, that someday soon everyone will be able to buy online. It's all part of a quest to understand the world in minute detail. One mystery scientists would love to solve is why some of the particles now whizzing around the universe have mass.
The fact is, from a physicist's point of view, from a philosopher's point of view, from an observational point of view, mass is actually quite mysterious.
In our best theory of matter, the Standard Model, all the really fundamental particles are like photons, the particles of light, in that they have no intrinsic mass. But we know that objects in the real world have mass, and scientists know that particles like protons and electrons also have mass. So where does that mass come from?
Why do particles have different masses, and why do they have mass at all? Mass is not something that emerges naturally from a theory.
We basically do not understand why some particles got mass and others didn't. What happened? What gave mass?
The leading idea for explaining mass is something called the Higgs field, a field which we believe pervades all of space and which the fundamental particles interact with.
The Higgs field is like cosmic cotton candy. It sticks to everything. And according to this idea, it's actually that stickiness that gives particles their mass.
If the Higgs field, along with a Higgs particle, really exists, then the Large Hadron Collider should find it. And that would be a triumph for the Standard Model. But since the LHC will take the particle hunt to a whole new level, many physicists are hoping it will uncover types of matter we've never even dreamed of.
The best case in my mind, we do not find a Higgs particle, and we find a whole new set of new particles.
I don't really care what we find. I just want to go off there and look at something and see something no one's ever seen before. That's what motivates me.
It's just a voyage of discovery. It's looking out into the cosmos and trying to see where we fit in it.